Hello there, and welcome to The Sleepy Astronaut, where curiosity meets comfort and science becomes something wonderfully approachable. Tonight, we're embarking on a soft journey into one of the most fascinating puzzles in all of physics. Can light truly be two things at once? Before we begin, can you comment where you're watching from? Also, let us know what time it is there. We love to hear people joining us from around the world to be a part of our community. Also, don't forget to leave a like and subscribe if you enjoy. Now, I do hope this exploration is engaging enough to hold your attention, but gentle enough to ease any intimidation you might feel about physics. Because somewhere between particles and waves, between certainty and mystery, lies one of the most beautiful stories science has to tell. So settle in, let your thoughts slow, and let's begin our quiet adventure into the dual nature of light. Light has always been a curious companion to humanity, hasn't it? It warms our days, illuminates our nights, and makes the very act of seeing possible. Yet for all its familiarity, light harbours secrets that have puzzled the greatest minds in science for centuries. The question of what light actually is has led us down paths both expected and wonderfully strange. And at the heart of this mystery lies something called wave-particle duality. The idea that light can behave as both a wave and a particle, depending on how we choose to observe it. Imagine, if you will, that you had a friend who appeared completely different depending on whether you met them at a coffee shop or at a library. Same person entirely, but somehow fundamentally different in each setting. That's rather like light. It shows us one face when we look for waves and an entirely different face when we look for particles. And remarkably, both faces are equally real, equally true. To understand this gentle paradox, we need to travel back through time to meet the brilliant minds who first grappled with light's mysterious nature. Perhaps more importantly, we need to understand why this matters. Why should we care whether light is a wave or a particle, or somehow miraculously both? The answer touches everything from the screen you're watching this on to the very nature of reality itself. Let's begin with waves, because waves are everywhere around us. They ripple across ponds, roll across oceans, and carry music to our ears. A wave is fundamentally a disturbance that travels through space and time, carrying energy without carrying matter. When you drop a pebble into still water, you create waves that spread outward in perfect circles. The water itself doesn't travel with the wave. It simply moves up and down as the wave passes through. Waves have some lovely characteristics. They have wavelength, the distance between two peaks, amplitude, how high the peaks are, and frequency, how many waves pass a given point in a certain amount of time. These properties give waves their personality. Short wavelengths might be energetic and quick, while long wavelengths are more leisurely and gentle. Now here's where it gets interesting. When waves encounter obstacles or openings, they do something rather magical. They diffract, bending around corners and spreading out. When they meet other waves, they interfere with each other, sometimes adding together to create bigger waves and sometimes cancelling each other out entirely. These behaviours are the signatures of waves, the calling cards that let us know we're dealing with something that spreads and flows and dances through space. For the longest time, scientists believed light was exactly this sort of wave, and they had good reasons to think so. Light seems to travel in straight lines, like ripples spreading from a source. It can be reflected off mirrors and refracted through prisms, breaking into beautiful rainbows of colour. Most convincingly, light appeared to diffract and interfere, just like water waves do. But then along came particles. And particles are quite different from waves. Where waves are spread out and flowing, particles are localized little packets of matter and energy that have definite positions and can be counted one by one. Imagine a handful of marbles. Each marble is distinct, separate, and you can point to exactly where each one is at any moment. Particles carry energy and momentum, but they do so in discrete chunks, not in the smooth, continuous way that waves do. When particles interact with obstacles, they don't diffract and spread like waves do. Instead, they bounce off or get absorbed. They follow predictable paths like tiny billiard balls, each with its own trajectory and destination. And when you measure particles, you get definite results. This particle is here, that one is there. No ambiguity, no spreading out, just solid, reliable, discrete little entities. So we have waves which are spread out and flowing, and particles which are localized and distinct, two completely different ways of being in the universe. For centuries, scientists assumed that everything, including light, had to be one or the other. The idea that something could be both seemed not just unlikely, but logically impossible. Yet as we developed more sophisticated ways of studying light, we began to encounter phenomena that couldn't be explained by thinking of light as purely a wave. Some experiments showed light behaving exactly like particles, discrete packets of energy that could be counted and measured. Other experiments showed light behaving exactly like waves, spreading and interfering, creating patterns that only waves could create. This wasn't a matter of incomplete understanding or experimental error. The evidence was clear and reproducible. Light genuinely behaves as both a wave and a particle, depending on the experimental setup. And this realization didn't come all at once, but gradually, through the work of many brilliant scientists, each adding pieces to a puzzle that seemed to defy common sense. The story of wave-particle duality is really a story about the limits of everyday intuition and the beautiful strangeness of the quantum world. We live in a middle-sized world where things are either waves or particles, where objects have definite positions and properties. But light inhabits a realm where such certainties dissolve into something far more subtle and mysterious. In our everyday experience, we never encounter anything that is both a wave and a particle. We see waves in water and particles like sand grains, but nothing that switches between these two modes of being. Yet light does exactly this. And in doing so, it reveals something profound about the nature of reality itself. That the universe, at its most fundamental level, operates according to principles that our everyday experience doesn't prepare us for. This isn't just an abstract philosophical curiosity. Wave-particle duality is the foundation of quantum mechanics, which in turn underlies all of modern technology, from the smartphone in your pocket, to the solar panels on rooftops, to the lasers that read barcodes at the grocery store. All of these technologies depend on our understanding of light's dual nature. But perhaps more importantly, wave-particle duality invites us to embrace a more flexible way of thinking about reality. Instead of insisting that things must be one way or another, we learn to hold multiple possibilities in our minds simultaneously. We learn that the question isn't whether light is really a wave or really a particle, but rather how we can best understand and work with its remarkable ability to be both. This gentle paradox at the heart of light's nature opens doors to wonders that we might never have imagined. It suggests that reality itself is far richer and more mysterious than our everyday experience suggests, and it reminds us that science at its best doesn't just give us answers, but teaches us to ask better questions and to remain open to possibilities that initially seem impossible. As we continue our exploration, we'll meet the scientists who first uncovered these mysteries. We'll see how light reveals its wave nature in some situations and its particle nature in others, and we'll discover why this seemingly abstract concept touches every aspect of our modern world. But for now, let's simply sit with this beautiful impossibility. That light, the thing that makes vision possible, is itself something that defies our usual categories of understanding. It's a reminder that the universe is full of gentle mysteries waiting to be discovered, and that sometimes the most profound truths are also the most wonderfully paradoxical. Now that we've explored the fundamental nature of wave-particle duality, let's delve deeper into the experiments that revealed this mysterious truth. Because understanding how light behaves requires more than just theory, it demands evidence. And the evidence, as we'll discover, is both elegant and deeply unsettling to our everyday understanding of reality. The story begins with a simple question that haunted physicists for centuries. If light is a wave, why does it sometimes behave like a stream of particles? The answer emerged through a series of experiments that would forever change our understanding of the universe. These weren't abstract mathematical proofs or philosophical arguments, but tangible demonstrations that anyone could witness and verify. Picture yourself in a darkened laboratory watching as a single beam of light encounters a barrier with two narrow slits. This is the famous double-slit experiment, perhaps the most important demonstration in all of quantum physics. When light passes through both slits simultaneously, it creates an interference pattern on a screen behind the barrier. Bright and dark bands appear, like ripples on a pond where two stones have been dropped. This is exactly what we'd expect from waves. They overlap, interfere, and create patterns. But here's where things become wonderfully strange. When we dim the light source until only individual photons pass through the apparatus one at a time, something remarkable happens. Each photon, travelling alone with no companions, still somehow creates the same interference pattern. How can a single particle interfere with itself? It's as if each photon passes through both slits simultaneously, existing in multiple places at once until it strikes the detection screen. This phenomenon suggests that light exists in what physicists call a superposition state. Before measurement, a photon isn't simply in one location or another, it's in a ghostly combination of all possible locations. The mathematics describe this as a wave function, a cloud of probabilities that encompasses every path the photon might take. Only when we actually observe or measure the photon does this wave function collapse into a single, definite outcome. The implications are staggering. Reality at the quantum level isn't made of solid, predictable objects moving along predetermined paths. Instead, it's constructed from possibilities, potentials, and probabilities that crystallize into concrete reality only when observed. It's as if the universe is constantly improvising, making decisions about what to become in the very moment we look. But the double-slit experiment reveals an even more puzzling aspect of quantum behavior. When scientists decided to peek behind the curtain and determine which slit each photon actually passes through, they installed detectors at each opening. The moment they began monitoring the photons' paths, the interference pattern vanished. The wave-like behavior disappeared, replaced by the simple, predictable pattern of particles passing through one slit or the other. This isn't a limitation of our measuring instruments or a quirk of experimental design. It's a fundamental feature of quantum mechanics called the measurement problem. The very act of observation changes the nature of what we're observing. Light behaves as a wave when we're not watching and as a particle when we are. It's as if reality itself is shy, revealing different aspects of its personality depending on how closely we're paying attention. The philosophical implications ripple outward like waves in a pond. If the act of measurement determines reality, what does that say about the nature of existence when no one is looking? Does the moon exist when nobody observes it? Einstein famously struggled with this question, declaring that he couldn't believe the universe was so fundamentally uncertain. Yet experiment after experiment has confirmed this strange dance between observer and observed. Consider the photoelectric effect, the phenomenon that earned Einstein his Nobel Prize. When light strikes a metal surface, it can knock electrons free from the atoms. Classical wave theory predicted that brighter light should always produce more energetic electrons, regardless of the light's color. But experiments showed something different. The energy of the ejected electrons depended not on the light's intensity, but on its frequency, its color. This made perfect sense if light consisted of discrete packets of energy called photons. Blue light, with its higher frequency, carries more energy per photon than red light. A single high-energy blue photon can knock an electron free, while even intense red light, composed of many low-energy photons, might not have enough punch per particle to do the job. The photoelectric effect revealed light's particle nature in a way that pure wave theory couldn't explain. Yet both experiments reveal authentic aspects of light's nature. The double-slit experiment showcases light's wave-like properties, interference, superposition, and the ability to be in multiple states simultaneously. The photoelectric effect demonstrates light's particle characteristics, discrete energy packets that behave like tiny billiard balls colliding with electrons. Neither view is wrong. Both are incomplete by themselves. This isn't a failure of science or a temporary confusion waiting to be resolved. Wave-particle duality is a feature of reality, not a bug in our understanding. Light genuinely is both wave and particle. Not sometimes one and sometimes the other, but always both in a way that transcends our everyday categories. The experiments also revealed something profound about the nature of scientific knowledge itself. We often think of science as gradually uncovering the true nature of reality, like archaeologists carefully brushing dirt away from ancient artifacts. But quantum mechanics suggests that reality might be more like a jazz performance, with the universe improvising its behavior in response to our questions. This doesn't mean science is arbitrary or that all interpretations are equally valid. The mathematics of quantum mechanics makes incredibly precise predictions, and experiments consistently confirm these predictions to extraordinary degrees of accuracy. But it does mean that reality is far stranger and more beautiful than our intuitions suggest. The wave-particle duality of light opened the door to understanding that all matter, not just light, exhibits this dual nature. Electrons, protons, atoms, and even molecules display wave-like properties under the right conditions. The universe is built from entities that refuse to be pinned down to simple categories, that exist in the spaces between our classical concepts. This isn't merely academic curiosity. Wave-particle duality underlies the technology that powers our modern world. Lasers rely on the wave nature of light to produce coherent beams. Solar panels depend on the photoelectric effect to convert sunlight into electricity. Computer chips exploit the wave-like properties of electrons to create the quantum tunneling effects that make modern electronics possible. Perhaps most remarkably, wave-particle duality hints at a deeper unity underlying apparent opposites. Just as light transcends the wave-particle distinction, reality itself might transcend many of the dualities we take for granted. The boundary between observer and observed, between mind and matter, between possibility and actuality, all become more fluid in the quantum realm. As we continue our exploration of light's mysterious nature, we'll discover that wave-particle duality is just the beginning. The quantum world holds even stranger phenomena, from entanglement to tunneling, from uncertainty principles to multiple realities. But the foundation remains the same. Reality is far more flexible, creative, and fundamentally mysterious than our everyday experience suggests. The experiments that revealed wave-particle duality didn't just change physics, they changed our understanding of what it means to exist in this universe. They showed us that the cosmos is not a machine made of solid, predictable parts, but something far more beautiful and strange. Now, let's dive deeper into what makes light's dual nature so genuinely extraordinary. Because here's the thing that often gets glossed over in textbooks and hurried explanations. Wave-particle duality isn't just a quirky footnote in physics. It's a fundamental principle that quietly underpins almost everything we understand about reality itself. And the more closely we examine it, the more it reveals about the curious, improvisational nature of existence. Think about it this way. In our everyday world, we're surrounded by categories that seem absolute. A chair is a chair, not a table. Water is liquid, not solid, unless you cool it down. Things have clear boundaries, definite properties, predictable behaviors. But light, that most familiar yet mysterious companion of our daily lives, simply refuses to be pinned down so neatly. When we say light behaves like a wave, we're not speaking metaphorically. It genuinely exhibits all the classic wave behaviors. It spreads out as it travels, just like ripples on a pond. It can bend around corners, a phenomenon called diffraction. When two light waves meet, they can interfere with each other, creating patterns of brightness and darkness that are the unmistakable signatures of waves interacting. This isn't just theory, it's something you can observe with a simple setup involving a laser pointer and a few household items. But then, in other circumstances, light behaves exactly like a stream of particles. These particles, called photons, carry discrete packets of energy. They can knock electrons loose from metals, a process that powers everything from solar panels to the light sensors in your camera. Each photon arrives at a specific place at a specific time, like a tiny billiard ball striking its target. This particle behavior is just as real, just as measurable, and just as fundamental as the wave behavior. What makes this truly mind-bending is that these aren't two different types of light. It's the same light, the same photons, the same electromagnetic radiation. The difference lies not in what light is, but in how we choose to observe it. When we set up an experiment designed to detect waves, we find waves. When we design an experiment to catch particles, we catch particles. It's as if light is somehow aware of what we're looking for and obliges us by becoming exactly that. This brings us to one of the most profound insights from quantum mechanics. The act of measurement isn't passive. In our everyday experience, we assume that observing something doesn't change it. You can look at a tree, measure its height, count its leaves, and the tree remains fundamentally unchanged by your attention. But at the quantum level, observation is participation. The very act of trying to pin down light's properties forces it to choose a particular identity. Before measurement, quantum objects exist in what physicists call superposition. They're not in one state or another, they're in all possible states simultaneously. A photon heading toward a detector isn't traveling as a wave or a particle, it's traveling as both, as neither, as a ghostly combination of possibilities. Only when we force it to interact with our measuring device does it collapse into a definite state. This isn't just true for light, it's a principle that governs the entire quantum world. Electrons don't have definite positions until we measure them. Atoms don't have definite energies until we force them to reveal their secrets. The universe at its most fundamental level is a realm of potential, of maybe, of not quite yet. Reality, in this view, isn't a fixed stage upon which events unfold, but rather a collaborative improvisation between the world and our attempts to know it. The implications ripple outward in ways that can be both unsettling and oddly comforting. If reality is fundamentally uncertain, fundamentally responsive to observation, then perhaps the universe is more flexible, more open to possibility than we usually imagine. Perhaps the boundary between observer and observed, between mind and matter, isn't as clear-cut as we've been taught to believe. This doesn't mean that reality is purely subjective or that we can think our way into different physical laws. The quantum world operates according to precise mathematical rules, and its effects are entirely predictable in a statistical sense. But it does suggest that the universe has a more participatory character than classical physics implied. We're not just passive observers of a mechanical cosmos, we're active participants in the ongoing creation of reality. Wave-particle duality also reveals something beautiful about the nature of complementarity. In quantum mechanics, complementarity is the idea that objects have pairs of properties that cannot be observed or measured simultaneously. For light, you can measure its wave properties or its particle properties, but not both at the same time. This isn't a limitation of our instruments, it's a fundamental feature of reality itself. Rather than seeing this as a frustrating limitation, we might view it as an invitation to embrace a more nuanced relationship with knowledge. Perhaps truth isn't always about having complete, simultaneous access to all properties of a system. Perhaps wisdom sometimes lies in accepting that different perspectives reveal different aspects of reality, and that the fullest understanding comes from holding multiple viewpoints in creative tension. This principle extends far beyond physics. In human relationships, we often discover that people can't be fully understood from any single perspective. A person might be simultaneously brave and fearful, generous and selfish, wise and foolish. These aren't contradictions to be resolved, but complementary aspects of a complex whole. The quantum world suggests that reality itself might be similarly multifaceted. The technology that surrounds us daily depends on our understanding of wave-particle duality. Lasers work because we can control light's wave properties to create coherent beams. Solar panels work because we can harness light's particle properties to generate electricity. LED lights work because we can engineer materials to emit photons with specific energies. Computer chips rely on our ability to manipulate electrons, which exhibit their own wave-particle duality. Every time you take a photograph, you're witnessing wave-particle duality in action. The light that bounces off your subject travels as waves, preserving information about color, brightness, and spatial relationships. But when that light hits your camera's sensor, it arrives as individual photons, each carrying a discrete packet of energy that gets converted into electrical signals and eventually into the pixels of your image. Even the simple act of seeing involves wave-particle duality. Light waves carry information from the world to your eyes, but that information is detected by your retina through the particle-like absorption of individual photons by light-sensitive molecules. Your vision is literally a quantum mechanical process, a daily miracle of wave-particle transformation. What's particularly fascinating is how wave-particle duality connects to the broader theme of emergence in nature. Just as consciousness emerges from the complex interactions of neurons and life emerges from the organized chemistry of cells, classical reality emerges from the quantum realm's fuzzy probabilities. The solid, predictable world we experience is built from components that are individually uncertain, probabilistic, and wonderfully strange. This emergence isn't just a one-way street. While quantum effects usually average out to produce classical behavior on larger scales, there are situations where quantum properties can manifest in surprisingly large systems. Scientists have observed quantum effects in objects visible to the naked eye, and there's growing evidence that quantum processes might play important roles in biological systems, from photosynthesis to possibly even consciousness itself. The story of wave-particle duality is ultimately a story about the limits and possibilities of human understanding. For centuries, we've tried to understand the world by breaking it down into categories, by drawing clear lines between this and that. But the quantum world suggests that reality might be more fluid, more contextual, more responsive to our presence than we ever imagined. This doesn't mean we should abandon logic or precision. Quantum mechanics is one of the most mathematically rigorous and experimentally successful theories in all of science. But it does suggest that our relationship with knowledge might need to be more humble, more flexible, more open to paradox and mystery. Wave-particle duality invites us to embrace what we might call quantum thinking, an approach to understanding that can hold contradictions without immediately rushing to resolve them. It suggests that sometimes the deepest truths can't be captured in simple either-or statements, but require a more nuanced both-and perspective. In the end, light's dual nature reflects something profound about existence itself. Reality isn't just a collection of fixed objects with predetermined properties. It's a dynamic, responsive, endlessly creative process in which possibility and actuality dance together in ways that are both mathematically precise and utterly mysterious. And we, as conscious observers, are not separate from this dance, but intimately woven into its steps. So the next time you flip a light switch, watch a sunset, or simply see the world around you, remember that you're witnessing one of the universe's most fundamental magic tricks. Light is simultaneously wave and particle, possibility and actuality, mystery and revelation. Now let's explore something quite profound that emerges from this mysterious duality of light. You see, the wave-particle nature of light isn't just some peculiar scientific curiosity tucked away in laboratory notebooks. It's actually the foundation upon which much of our modern world quietly rests, humming along in ways that might surprise you. Consider for a moment the device you're likely using to listen to this very explanation. Whether it's a smartphone, tablet, or computer, deep within its circuits lies a phenomenon that depends entirely on light's particle nature. The photoelectric effect, which Einstein won his Nobel Prize for explaining, is what makes solar panels work. When photons strike the solar cells, they knock electrons loose, creating the electrical current that powers everything from calculators to space stations. Without understanding light as particles, we'd still be burning candles for illumination and wondering why certain metals spark when light hits them. But then, just as beautifully, light's wave nature gives us an entirely different set of technological marvels. Every time you stream a video, send a text message, or make a phone call, you're relying on electromagnetic waves. Radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays are all part of the same electromagnetic spectrum, all manifestations of light's wave-like character. The wireless signals carrying your data are literally waves of light, though invisible to our eyes, rippling through space at the speed of light itself. In medical imaging, we see this duality at work in remarkable ways. X-rays, behaving as high-energy photons, can penetrate soft tissue, but are absorbed by denser materials like bones, creating the shadow images that help doctors peer inside our bodies. Meanwhile, MRI machines use radio waves, exploiting the wave properties of electromagnetic radiation to create detailed images of our internal structures. It's as if light keeps a comprehensive toolkit, switching between its wave and particle personas depending on what needs to be accomplished. The laser, that marvel of modern technology, represents perhaps the most elegant demonstration of light's wave nature, harnessed for practical purposes. Inside a laser, light waves are coaxed into moving in perfect synchronization, all peaks and troughs aligned, creating a beam of extraordinary coherence and intensity. This synchronized wave behavior allows lasers to cut through steel, perform delicate eye surgery, read the tiny pits on a DVD, and even measure the distance to the moon with incredible precision. The Apollo missions left reflectors on the lunar surface, and scientists still bounce laser beams off them today, timing the round trip to track how the moon's orbit changes over time. But here's where it gets truly fascinating. In quantum computing, researchers are attempting to harness the most mysterious aspects of wave-particle duality to create machines that could revolutionize how we process information. Quantum computers rely on the principle that particles can exist in multiple states simultaneously, that strange quantum superposition we touched upon earlier. A quantum bit or qubit can be both 0 and 1 at the same time, existing in a ghostly combination of possibilities until measured. This allows quantum computers to explore many potential solutions to a problem simultaneously, potentially solving certain types of calculations exponentially faster than conventional computers. The technology in fiber optic cables, those hair-thin strands of glass that carry the internet around the world, depends on a delicate dance between light's wave and particle properties. Light pulses, behaving as photons, carry digital information by being present or absent, creating the ones and zeros of binary code. But these same light pulses travel as waves, bouncing down the length of the fiber through a process called total internal reflection. The wave nature of light ensures that signals can travel vast distances with minimal loss, while the particle nature allows for the discrete, countable pulses that represent digital information. In the realm of astronomy, telescopes capture light that has travelled for billions of years across the universe, and both aspects of light's nature are crucial to what we can learn. The wave properties of light allow us to build interferometers, devices that combine light from multiple telescopes to create images with the resolution of a much larger telescope. The particle properties help us understand the energy of cosmic rays and the processes happening in distant stars. When we detect light from the most distant galaxies, we're literally catching photons that began their journey when the universe was young, each one a tiny messenger carrying information across cosmic time. Photography, from the earliest daguerreotypes to modern digital cameras, has always relied on light's particle nature. Individual photons strike light-sensitive materials or sensors, each one contributing to the final image. The graininess you might notice in photos taken in low light conditions is actually the result of having too few photons to create a smooth image, a direct reminder that light comes in discrete packets. Even the humble LED light bulb in your home operates on principles derived from our understanding of light's dual nature. Electrons in the semiconductor material jump between energy levels, emitting photons in the process. The color of the light depends on the energy difference between these levels, with each photon carrying a specific amount of energy that determines whether we see red, blue, green, or any other color. It's quantum mechanics made practical, sitting quietly in your living room, turning electricity into light one photon at a time. Perhaps most remarkably, GPS satellites orbiting Earth must account for relativistic effects that influence both the wave and particle aspects of the electromagnetic signals they transmit. The precise timing required for GPS to work depends on understanding how light propagates through space and time, taking into account the subtle ways that gravity and motion affect the passage of time itself. Without these corrections, your navigation system would be off by several kilometers within minutes. The screens displaying this information, whether LCD, OLED, or e-ink, all manipulate light in sophisticated ways. LCD screens use liquid crystals that can rotate the polarization of light waves, combined with color filters and backlighting to create images. OLED screens generate their own light through electroluminescence, with individual pixels emitting photons directly. Even the simple act of reading words on a screen involves countless photons traveling from the display to your eyes, where they trigger chemical reactions in your retina that your brain interprets as text. In scientific research, tools like electron microscopes reveal the wave nature of matter itself. Just as light exhibits wave-particle duality, so do electrons, and this wave-like behavior of electrons allows us to create images at scales far smaller than what's possible with light-based microscopes. It's a beautiful symmetry, using the wave properties of one type of particle to study the structure of others. All of these technologies, from the most mundane to the most sophisticated, rest on the fundamental understanding that light is not confined to being just one thing. It's both wave and particle, both spread out and localized, both predictable and mysterious. This duality isn't a limitation or a confusion in our understanding. It's actually the key that unlocks countless possibilities. As you go about your daily life surrounded by devices and technologies that depend on light's dual nature, perhaps you'll pause for a moment to appreciate the profound strangeness underlying the ordinary. That smartphone in your pocket, the GPS guiding your journey, the internet connecting you to the world, the very screens displaying information, all of these represent humanity's growing fluency in the language of light's duality. We've learned to speak to both aspects of light's nature, to coax waves into coherent beams, and to count individual photons, to harness electromagnetic fields, and to manipulate quantum states. In doing so, we've not just built a technological civilization, we've developed a deeper conversation with the fundamental nature of reality itself. And this conversation is far from over. As our understanding of wave-particle duality continues to evolve, so too will our ability to create technologies that seem almost magical today. Now that we've journeyed through the fundamental mysteries of wave-particle duality, witnessed how observation shapes reality, and explored the technological marvels that spring from understanding light's dual nature, we arrive at perhaps the most profound question of all. What does this paradox teach us about the nature of reality itself? Because when we step back and consider what we've discovered, we're not just learning about photons and electrons. We're uncovering something far more fundamental about the universe we inhabit. The wave-particle duality of light isn't simply a curious quirk of quantum mechanics that scientists debate in ivory towers. It's a window into the very fabric of existence, revealing that reality operates on principles that challenge our most basic assumptions about how things work. When we discovered that light behaves as both wave and particle, depending on how we observe it, we didn't just solve a physics puzzle. We stumbled upon a truth that reshapes our understanding of observation, measurement, and the role consciousness plays in the cosmos. Think about what this means for a moment. In our everyday experience, objects have definite properties whether we're looking at them or not. A chair remains a chair, a tree stays rooted in its spot, and your morning coffee maintains its temperature regardless of whether you're paying attention to it. But light, and indeed all quantum particles, exist in a fundamentally different realm where properties aren't fixed until the moment of observation. This isn't just strange, it's revolutionary. It suggests that the act of measurement doesn't simply reveal pre-existing properties, but actually participates in creating them. This participatory aspect of reality extends far beyond laboratory experiments. When we understand that observation influences outcomes at the quantum level, we begin to see that the universe isn't a collection of separate objects bumping into each other like billiard balls. Instead, it's an interconnected web where the observer and the observed are intimately entangled. The old notion of objective reality existing independently of consciousness starts to wobble. We're not passive witnesses to the universe, we're active participants in its unfolding. The implications ripple outward in fascinating ways. If consciousness plays a role in shaping reality at the quantum level, what does that mean for our understanding of free will, choice, and the nature of experience itself? Some interpretations of quantum mechanics suggest that consciousness might be more fundamental than we previously imagined. Not just an emergent property of complex brains, but something woven into the very structure of reality. Now, this doesn't mean we can think our way into changing the laws of physics or manifest parking spaces through positive thinking. The quantum world operates according to strict mathematical principles and probabilities. But it does suggest that the relationship between mind and matter might be more intimate than classical physics ever imagined. Wave-particle duality also teaches us about the limits of language and conceptual thinking. We struggle to describe light's dual nature because our words and concepts evolved to handle the classical world of everyday experience. We say light is both wave and particle, but that's not quite right. Light is something that transcends both categories, something that can manifest as either depending on the context of observation. This points to a deeper truth about reality. It's richer and more nuanced than our conceptual frameworks can fully capture. This has profound implications for how we approach knowledge and understanding. The complementarity principle, introduced by Niels Bohr, suggests that different aspects of reality can only be revealed through different types of observation. Wave properties emerge through wave-detecting experiments, particle properties through particle-detecting experiments. Neither gives us the complete picture alone. Only by embracing both perspectives do we begin to glimpse the fuller truth. This principle extends beyond physics into philosophy, psychology, and even daily life. Perhaps human nature itself exhibits complementarity. We might be simultaneously individual and collective, rational and emotional, determined and free, depending on the lens through which we observe ourselves. The mystics and poets have long intuited this multiplicity of being, and quantum mechanics provides a scientific framework for understanding how apparent contradictions can coexist as aspects of a deeper unity. The duality of light also illuminates the relationship between certainty and uncertainty. Heisenberg's uncertainty principle tells us that there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. The more precisely we measure light's position, the less precisely we can know its momentum, and vice versa. This isn't a limitation of our measuring instruments, but a fundamental feature of reality itself. Uncertainty isn't a bug in the system, it's a feature. This built-in uncertainty creates space for possibility and creativity. If everything were completely determined and predictable, there would be no room for novelty, evolution, or genuine choice. The quantum realm's inherent uncertainty might be what allows for the emergence of new forms, new patterns, new possibilities. In a strange way, uncertainty becomes the foundation for freedom. The wave-particle duality also speaks to the importance of context in determining reality. Light doesn't have an inherent nature independent of its environment and the way it's observed. Its properties emerge from the relationship between the light, the experimental setup, and the observer. This relational view of reality suggests that nothing exists in isolation. Everything is what it is because of its relationships and connections with everything else. This interconnectedness challenges the notion of separate, independent objects and points toward a more holistic understanding of existence. Indigenous wisdom traditions have long understood this interconnectedness, seeing the world as a web of relationships rather than a collection of isolated things. Quantum mechanics, in its own way, arrives at a similar understanding through rigorous mathematical analysis and careful experimentation. Perhaps most remarkably, wave-particle duality reveals the fundamental role of paradox in nature. We're accustomed to thinking in terms of either-or logic. Something is either a wave or a particle, either here or there, either true or false. But quantum mechanics introduces us to both and logic. Light is both wave and particle. Particles can be in multiple states simultaneously, and observation both reveals and creates reality. This acceptance of paradox as a fundamental feature of reality, rather than a problem to be solved, opens up new ways of thinking about existence. It suggests that the deepest truths might not be reducible to simple, non-contradictory statements, but might require us to hold multiple perspectives simultaneously. The ancient Eastern concept of the middle way, which transcends the extremes of opposing viewpoints, finds unexpected resonance in quantum mechanics. As we conclude our exploration of wave-particle duality, we're left with a profound sense of wonder and humility. Light, this most familiar phenomenon that illuminates our days and enables our vision, turns out to be far more mysterious and sophisticated than we ever imagined. It serves as a gateway to understanding the quantum realm, where the rules of reality are written in the language of probability, complementarity, and paradox. The duality of light reminds us that the universe is not only stranger than we imagine, but perhaps stranger than we can imagine. It challenges us to expand our thinking, to embrace uncertainty and paradox, and to recognize our deep interconnection with the cosmos we inhabit. In learning about light's dual nature, we discover something essential about the nature of reality itself. It's participatory, relational, and fundamentally mysterious. And perhaps that's the most beautiful revelation of all. In a universe where light can be both wave and particle, where observation shapes reality, and where consciousness plays a role in the cosmic dance, we find ourselves not as separate observers looking in from the outside, but as integral participants in the ongoing creation of reality. We are the universe becoming aware of itself, consciousness emerging from the quantum foam to contemplate its own mysterious nature. The wave-particle duality of light isn't just a chapter in physics textbooks. So here we are, dear friends, at the end of our gentle exploration into the nature of light itself. We've wandered through laboratories where single photons dance through slits, creating patterns that shouldn't exist according to our everyday understanding. We've marveled at the photoelectric effect, where light knocks electrons from metal surfaces like tiny billiard balls, defying the wave-like behavior we just witnessed moments before. And we've stood at the edge of one of physics' most profound mysteries, watching light refuse to be pinned down to a single identity. But perhaps that's exactly the point. Perhaps the lesson isn't that light is broken or confused, but that our need to categorize everything into neat, separate boxes is what creates the confusion in the first place. Light simply is what it is, expressing itself as waves when we look for waves, as particles when we look for particles, and as something beautifully indefinable when we step back and appreciate the whole picture. This wave-particle duality isn't just a curiosity tucked away in physics textbooks. It's woven into the fabric of our modern world in ways both subtle and profound. Every time you charge your phone with a solar panel, you're witnessing the particle nature of light, as photons knock electrons loose to create electrical current. Every time you watch a movie projected onto a screen, you're seeing the wave nature of light as it diffracts around tiny obstacles and interferes with itself to create the images that tell stories. The lasers that read your music, the fiber optic cables that carry your messages across oceans, the quantum computers that may one day solve problems we can barely imagine today. All of these technologies spring from our understanding that light can be two things at once. They work not despite this duality, but because of it. And there's something deeply comforting about that, isn't there? In a world that often demands we choose sides, pick categories, and declare allegiances, light quietly demonstrates that identity can be fluid, contextual, and beautifully paradoxical. It suggests that perhaps the richest understanding comes not from forcing things into rigid definitions, but from allowing them to be complex, multifaceted, and even contradictory. The quantum world, of which light is such a perfect ambassador, operates on principles that challenge our classical intuitions. Superposition tells us that particles can exist in multiple states simultaneously until observed. And complementarity, the principle that encompasses wave-particle duality, reminds us that complete understanding sometimes requires holding multiple perspectives simultaneously. These aren't just abstract concepts floating in the realm of theoretical physics. They're fundamental features of reality that shape everything from the colour of flowers to the structure of DNA, from the warmth of starlight to the intricate dance of photosynthesis that sustains life on Earth. The quantum world isn't separate from our world, it is our world, seen clearly. But here's what I find most remarkable about wave-particle duality. It suggests that reality is participatory. The act of observation, of measurement, of asking specific questions about light's nature actually influences what we find. It's not that light is secretly a wave pretending to be a particle, or vice versa. It's that the very act of looking shapes what we see. This has profound implications that ripple far beyond the laboratory. It suggests that consciousness, observation, and reality are more intimately connected than we might have imagined. It hints that the universe might not be a collection of objects existing independently of observers, but rather a web of relationships, interactions, and mutual influences. When we observe light behaving as a wave, we're not just passive recipients of information. We're participants in a cosmic conversation, asking questions through our experimental setups and receiving answers that reflect both the nature of light and the nature of our questioning. The double-slit experiment doesn't just reveal something about photons, it reveals something about the relationship between mind and matter, between observer and observed. This participatory aspect of reality extends beyond physics into philosophy, consciousness studies, and even our daily experience. How often do we find that our expectations, our attention, our very way of looking at a situation influences what we discover? How often do we realize that the questions we ask shape the answers we receive? Wave-particle duality invites us to embrace uncertainty not as a limitation, but as a gateway to deeper understanding. It suggests that the most profound truths might not be found in definitive answers, but in the graceful dance between seemingly contradictory perspectives. It teaches us that reality is rich enough to support multiple valid viewpoints simultaneously. And perhaps that's the most beautiful lesson of all. In a world that often feels fragmented and polarized, light shows us a different way. It demonstrates that unity and diversity aren't opposites, but complementary aspects of a richer whole. It reveals that the deepest truths often emerge not from choosing between alternatives, but from discovering how apparent opposites can coexist and even enhance each other. So as we conclude our journey through the mysterious nature of light, let's carry this wisdom forward. Let's remember that, like light itself, we too can be many things at once. We can be logical and intuitive, scientific and spiritual, grounded and transcendent. We can embrace both the particle-like clarity of focused attention and the wave-like expansiveness of open awareness. The next time you see sunlight streaming through a window, casting shadows and illuminating dust motes dancing in the air, remember that you're witnessing one of the universe's most elegant demonstrations of how something can be simultaneously simple and complex, familiar and mysterious, knowable and ineffable. Light teaches us that reality is not a problem to be solved, but a mystery to be lived. It shows us that the deepest understanding often comes not from forcing things into rigid categories, but from allowing them to be exactly what they are in all their paradoxical glory. And in that allowance, in that gentle acceptance of mystery, we find not confusion but clarity, not limitation but liberation, not the end of understanding but the beginning of wisdom. Light, in all its wave-particle duality, reminds us that the universe is far more wonderful, far more interconnected, and far more alive than our everyday concepts might suggest. So let us rest in that wonder, dear friends, and let the gentle mystery of light carry us softly into our dreams, where perhaps we too can be waves and particles, possibilities and actualities, questions and answers, all dancing together in the beautiful, inexplicable choreography of existence. We hope you enjoyed learning tonight. Before we end our journey, can you comment where you're watching from? Also, let us know what time it is there. We love to hear people joining us from around the world to be a part of our community. Also, don't forget to leave a like and subscribe if you enjoy this story. Good night, fellow space explorer.